Hello everyone, welcome to chapter 4. We have derivatives and the shape of a graph here. Sometimes it's also known as monotonic functions. The shape of the graph is determined using concavity and curve sketching. So these are different names you'll see based on the textbook and the homework types that you see. And so we're going to look into uh, the, uh, the ways in which we could use derivatives to determine the shape of a graph and be able to sketch a graph just by looking at the function. Let me start with this definition, monotonic. Mono means single, right? Mono, stereo, monotonous. So mono means single, something the same way. And in this case, monotonic functions typically defines a function that is increasing or decreasing. So it takes the same direction, right? If it's monotonic, it's in the over a particular interval. Is it increasing or is it decreasing? So the definition above here says, suppose that f is continuous on AB and differentiable on interior of AB. That's the premise. If f prime of x, meaning the first derivative, is positive, greater than 0, at each point x that belongs to AB, then f is increasing on AB. If f prime of x is less than 0 at each point x in AB, then f is decreasing on AB. We can see that the derivative indicates the increasing, decreasing. Again, this is not new to us because we've seen that. In fact, when we spoke about lines, we said if the slope is positive, it implies the line is increasing. And if the slope is negative, it implies the line is decreasing. We've seen that. So the same idea, just that we're not looking at a specific line or only linear functions here. It's open to any function f that is continuous on AB, closed interval AB, and differentiable on open interval AB. If that's the case, we're saying if you can determine over a particular interval that every point in x, that for every point in x, the derivative is positive, then you know it's increasing, the function is increasing. And if it's less than 0, the slope is less than 0, then the function is decreasing. Very straightforward. So let's take a look at an example to kind of identify this. Find the critical points of f of x cubed minus 12x minus 5, and identify the open intervals on which f is increasing and on which f is decreasing. Okay, so f of x is given to be x cubed minus 12x minus 5. This is a polynomial of degree 3, so that means this implies polynomial of degree 3. That means it is going to be continuous everywhere, right? Doesn't work only for a particular interval. In fact, it works throughout. And that means it's differentiable everywhere. We know this because they didn't give us an interval, so we are trying to see for the entire domain, and it works. Now, because of this, we can find the first derivative because it's differentiable everywhere. And take the derivative here. That's going to be 3x squared minus 12. Okay. And what we know is that if we find the critical points, we can then determine, because critical points will help us to will tell us where this f prime will be 0. And so we want to find out where it's going to be less than 0, where it's going to be more than 0. So it will give us a point where we can break the interval. So to find the critical points, we need to set this f prime of x to be equal to 0. And that means 3x squared minus 12 equals 0. As always, do your GCF, which is x squared minus 4, and then factorize it. Apologize, x plus 2, x minus 2. Okay, because a plus b, a minus b. Now this implies your x, when you set each x to 0, you get minus 2 and 2. These are the two critical points. Now this helps us to split up our interval because we said it's continuous everywhere throughout the domain. So we can now draw our number line and split it up based on these critical points. Okay. So these critical points will tell me that at -2 and at 2, we have kind of a split happening. Because at these 2 points, f prime of x is 0. So I need to know what's happening to the from -infinity to -2, what happens between these two, -2 to 2, and from 2 to infinity. Okay. So what I'd like to do is build some kind of a table here underneath. Let's say intervals. So this first interval is -infinity to -2. We want open intervals because that was part of the instruction. Because if you included -2, that's exactly 0. But the rule, I'll take you back here. The rule says strictly greater than 0, which means it has to be positive or negative. It can't be equal to 0 for those conditions, for the increasing, decreasing conditions. Then this is -2 to 2, and this is from 2 to infinity. So now what we do is we will choose a test point from each interval and determine the sign of f prime, because if it's positive or negative, that will help us to determine the behavior, whether it's increasing or decreasing. So then I will say test point. You could choose any value that is nice for us to use. So what I'd like to do here is use the test point of -3 maybe, yeah, right, for this interval. And for this interval, 0 is the best choice. And here we can choose 3. So find f prime. So f prime of -3, go back and plug it in the equation, right? The equation for f prime was 3x squared minus 12. So plug in -3 here. -3 squared, the whole square, will be +9. 9 times 3, 27. 27 minus 12, +15. Then we have f prime of 0. When you do the f prime of 0, you get -12. So let's write that. And f prime of 3, if you go back here, 3 has to be squared. So it is as if you did the -3, the whole squared, because 3 squared comes back as +9. 9 times 3, 27, minus 12, 15. So you get the same information here. Okay. What is the sign of f prime? Here it is positive. In this interval, it's negative. In this interval, it is positive. So then I have another one. Behavior of f. Now, the sign of f prime actually tells you how f behaves. Okay, the behavior is for the function, not for the derivative. The derivative only helps you to determine that behavior. So then I come back here and I say, okay, now we saw that we had -2 here, +2 here. And we could see that in this interval, right, and in this interval, these two were increasing. And this middle interval, -2 to 2, the function is decreasing. So this is a graphical representation, but then if they wanted you to give out the intervals specifically, then this is how we will write it. Say the function f is increasing on -infinity to -2 union 2 to infinity, because you have the two intervals with a gap in between. When there is a gap, you bring in the union symbol to kind of link or chain the two disjoint intervals. Then we say the function f is decreasing on -2 to 2. Please do not include the end points because it's on the interior that we're talking about. I put up the graph for this, and as you can see, the intervals, without having a view at the graph, we were able to do this just by using the first derivative, where we determined that from negative infinity all the way up to negative 2, the graph was increasing, right? It's climbing up. From left to right, the graph rises. And again, that was the case from 2 to infinity, where the I hope that's better. Then from 2 to infinity, see the graph rising here. Yeah. And the graph was decreasing in between them from negative 2 to 2. And you can see the graph was falling in this region. Now, based on this, we now have a first derivative test for local extrema. What we saw previously was called the first derivative theorem, and this is actually a test. So let's read this. Suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C. Moving across this interval from left to right, 1. If f prime changes from negative to positive at C, then f has a local minimum at C. If f prime changes from positive to negative at C, then f has a local maximum at C. And f prime does not change sign at C, that is, f prime is positive on both sides of C or negative on both sides, and it has no local extremum at C. So that's really interesting. So we have really cool ways to find or use this as a test, the first derivative test, to find the local extrema. Now, the first derivative theorem said if there is a local extremum, like a local minimum or a local maximum, then f prime of C is 0. So that's what we're using. So if you use critical point, C is a critical point, that means f prime of C is 0 at those points, right, for that C. So that means just like what we did, we use that as the interval to break our number line based on the C, C1, C2, how many ever critical points we may have. And then we're saying, well, if f prime changes sign, we saw how the sign, in fact, here we saw the sign of f prime, right? So we're saying if it changes sign from positive to negative, it means something, and from negative to positive, it means something. So let's check it out here. If f prime changes from negative to positive, then f has a local minimum at C. So from f prime, from negative to positive. So you can see that here, it moved from negative to positive, right? That means there was a minimum. And if you come back to the graph, you can clearly see that that is the case. It has a local minimum. Whether it's an absolute minimum, that's different. But in this case, definitely it's a local minimum because our graph continues to stretch further down. So this is not the lowest point, right? So there is a local minimum. And if f prime changes from positive to negative at C, then f has a local maximum at C. So coming back here, it changes from positive to negative at negative 2, right? That's where it changes. That means it has a local maximum at negative 2, and that is supported here. At negative 2, there is a local maximum. There is a peak that you can see. And we're saying if it does not change sign at all, at C, so if it continues to go the same direction, positive, and continues on as positive, or if it is going down negative, it continues further as negative, then there is no local extremum at C. To illustrate this, I have the following graph. We've seen a similar graph when we were talking about absolute maximum, absolute minimum. So let's take a look at this. Okay. So now we have this as the endpoints. These are the endpoints. Right? So among all these points, this is the lowest. So that's the absolute minimum. A is where the absolute minimum occurs. And if you look at the entire graph among all of these, this is the maximum point, right? So C4 is where the absolute maximum occurs. Okay. All right. And all other peaks and low points is where you'll have the possible extremum. Now, we do have the understanding now with this first derivative test that if, now that we determine the absolute max and absolute min, we now have to see if we can use the first derivative test to determine local extrema. So then, for that, we need to find the first set the first derivative to 0. Right? So we set the first derivative to 0. Oops, for f prime of x to be 0. And whatever values you get, we know that that's where it is, where the critical points are. So based on this graph here, we see that it is 0 at C1, f prime is 0 at C1, C2, C3, and C5. Isn't it? So these are the places where we see f prime to be 0. So we found the critical points. Now we need to know if there is a presence of local extrema. Now we look at C1. So then C1 is kind of helping us to determine what happens before C1 and after C1. So choose a test point in this interval A to C1 and plug it in your function. Now we're not given a function, so we just have to look at it from the graph. So then we have to read the graph from left to right. From A to C1, from left to right, does your graph increase? Meaning, does the slope increase, right? You're basically looking for the tangent line. Yes, the slope is increasing, so that is good. So f prime is positive from A to C1. From C1 to C2 to the next point, see what happens. We see that, once again, if you had the function given to you, you can take the first derivative and plug in a test point there. Or if it's a graph like this, then you want to check it in terms of the derivatives, right? The slope. And you see that it's increasing. So from left to right, the graph rises. What we see there, though, is that at C1, the graph rises and continues to rise. There was no change in sign from before C1 and after C1, right? So let's say at C1, no change in sign of f prime. That is why we say no extremum, because that is the third point here in this test. If f prime does not change sign at C, then f has no local extremum at C. So we got that. Next we go to C2 and do the same thing. So before C2, that is between C1 and C2, if you performed it, we just saw that, in fact, that was positive. F prime was positive. And then from C2 to C3, it is negative. So at C2 changes, I'll say f prime. F prime changes from positive to negative. That implies that there will be a local max at C2. And we can see that there's a local max at C2. Then at C3, that was their next critical point. At C3, f prime changes from negative to positive, right? Negative here and then positive here. So it's making a U-turn. So you do have a local min at C3. Then we move to the last one, C5. C5, to the left of C5, from C4 to C5, f prime is negative, right? It falls. And then from C5 to B, it continues to fall. So no change in sign of f prime. This implies no extremum at C5. And that is how we use the first derivative test to determine the presence of local extremum. Find the critical points of f of x equals x power 1/3 times x minus 4, and they expanded it for us. Identify the open intervals on which f is increasing and decreasing, and find the function's local and absolute extreme values. Two things to do here. Okay. So one is, of course, to find the increasing, decreasing based on the sign of the first derivative. And then again, using the sign change of the first derivative, we find the local and absolute extreme values. All right, let's start off with this is given to us. It's good to have it in this factored form, so let's hold on to that, as well as the distribution. When you distribute, you add the powers. So that's how you get this power here is 1. 1/3 plus 1 is 4/3. minus 4 times x power 1 over 3. Now, this will be helpful for us to do the derivative, to take the derivative. The expanded form helps with the derivative. F prime of x is 4 over 3, x power 4 over 3 minus 1, minus 4 times 1 over 3, x power 1 over 3 minus 1. Okay. So that's 4 over 3, x power 1 over 3, minus 4 over 3, x power negative 2 over 3. So what I'd like to do is pull out the 4 over 3. Okay. Now we need to find the critical points, right? That was the question, find the critical points, because we need to do that to break our interval based on the critical points. So in order to set this to 0, we can't just keep it in this form. So I'd like to put it as a single fraction. So I take the LCD, okay? So then basically I'm cross multiplying to show, because it's got rational powers, I'd like to show this operation here. So it's the same thing what you do for LCD, it's just that it's got this extra term, I would say. Multiply up and down by x power 2 over 3. And that's what I mean when I take the LCD. Then add the powers. 2 plus 1, 3. 3 over 3 is 1. So you have 4 over 3, x minus 1 over x power 2 over 3. I hope you can see that. And now critical points implies you have to set your first derivative to 0. This implies I have to set 4 over 3 x minus 1 over x power 2 over 3 to 0. So there are two things I have to do. Okay, critical points is, of course, where f prime is 0, and also when the derivative is undefined. So we have to, because it's a rational setup, that's what we need to do. And we've done a similar problem like this when I introduced critical points. So here I'm going to set the numerator to 0. Implies that x minus 1 is 0, because you can't set the 4 over 3 to 0, you know that. So this means x equals 1. And if you set the denominator to 0, we see that when x is 0, that's when the denominator is 0. So then this is where f prime is 0, and this is where f prime is undefined. Both of these give us the critical points. So we got these two. Now let's go ahead and break our interval, or number line I should say, into intervals. So we have 0, and then we have 1. For convenience, I'm going to mark negative infinity, infinity, because it helps us to write out the intervals, right? So we now have the intervals will be negative infinity to 0, 0 to 1, and 1 to infinity. In fact, you have to come up with a test point. You can save time by just doing all that in the background and just look at the sign of f, but it's not a problem. Let's choose a test point here. And again, anything will work. So let's say negative 1 was your choice. Here it's between 0 and 1. Perhaps half was your choice. And here you could use 2. Okay. Plug that in your f prime. We are really interested in the sign, not necessarily the answer. I'm not looking for the number, I'm looking for the sign. And therefore what I get here is negative. This again gives me negative, and this gives me positive. Okay, I'd like you to pause the video and compute this to verify it. That means if we talk about the behavior of f, sign of f prime helps you understand the behavior of f. And we see that because it's minus, right? It's decreasing. The function is decreasing. The function is increasing in this interval. But if we were to find the function's local and absolute extreme values, it goes from decreasing to decreasing, right? It goes decreasing to decreasing. That means at 0, there is no extremum because there was no change there. From decreasing to increasing, there was a change in sign. So I want to go back here, decreasing to increasing, minus to plus. Minus to plus. When it changes from negative to positive, there's a local minimum at C. So then I come back here and say, okay, there is a local minimum at 1. Now, if you want to, of course, we can come back here and show it on the graph if you wanted, that this is the place where it increases. And these two intervals, it was decreasing. So if you were to write it as an interval, you can say negative infinity all the way to 1, it was decreasing, and it was increasing from 1 to infinity. So here is the graph for this function. And as you can see, from negative infinity all the way to 1, as we determined, the function is decreasing, right? It's decreasing all the way. And from 1 to infinity, it's increasing. So let me just show that portion here. This portion here, sorry, it's getting messy. This portion here is decreasing, and this portion here is increasing. So we can see that. But we also, let me clear this. We also see that the portion where, or rather at 0, where we said there is no extremum, right, actually has a vertical tangent. Isn't it? If you were to draw the tangent through that point, it's going to be a vertical tangent because that's the way it can touch the blue graph and the vertical tangent. Now, we also said there is a local minimum at 1, right? We need to determine what the coordinate is because we need to find the value for that local minimum. So in your f function, if you plugged in 1, so you have 1 power 1 over 3 times 1 minus 4. That would be 1 times negative 3, just negative 3. You see that that is what you have here. There is a local minimum, which is happening here. In the case of this graph, this is your absolute minimum as well. But remember, this test is helping us to find the local minimum. It happens here that it's also the absolute minimum. And so it really worked out nicely for us. And we can see that, from on a graph because you get to get the full view of this function. But here we know that that is the case because of the critical points. Within the interval 0 to 2 pi, find the critical points of f of x, which is a trig function. Identify the open intervals on which f is increasing and decreasing, and find the local and absolute extreme values. Okay. We have f of x given to be sine squared x minus sine x minus 1. And our interval, this inequality notation can be written as an interval notation like this, right? And it's closed interval because of the less than or equal to bar in the inequality. So first we need to find the critical points. Take the derivative here, and or always remember chain rule kicks in. So derivative of the outside times derivative of the inside, derivative of sine x is cosine x minus cosine x minus z. critical points implies you want to set your derivative to 0. Oops, there's one more. Minus cosine x equals 0. And now we can pull out the GCF, which is cosine x. You always have to do that. Let me just quickly remind you, I said this in a different video, but what sometimes students tend to do is add cosine x on both sides. Okay, this is wrong, so I'm showing you why it will be wrong. Okay, you have something like this. And your next tendency is to obviously divide both sides by cosine x, right? So then you'll have 2 sine x equals 1. Then you'll say sine x equals half. And you just get the information just for the sine x part because you cancelled away the cosine x. On the other hand, so this is completely wrong. You should never do that. You always have to do the GCF. You need to factor out. Okay. And I'll erase this. Because what you'll see now in this step is when I have factored out each one of them, then you set the cosine x equal to 0. You also set the other factor. So you set each factor to 0. So your cosine x is not lost. Its value is very important, as you see now, because actually it gives us two x values, 2 angles where cosine x will be 0. Okay. So this implies cosine x will be 0 at 90 degrees and at 270 degrees. So in other words, in radians, it will be at pi over 2 and 3 pi over 2. Okay, that's for this. And here, sine x equals half, right? Add 1 on both sides and divide by 2. That means your x, meaning sine x, will be half at pi over 6 and 5 pi over 6. You can look at the unit circle to get this information, and thankfully your interval is from 0 to 2 pi, so it's just one rotation that you're looking at. So we got that. Okay, now you've got 1, 2, 3, 4. Okay, if you were to line them up as per their value order, because you need, these are your critical points, you need to line them up. So I'm going to write the critical points in ascending order. It's so important to put them in order. Pi over 6, pi over 2, 5 pi over 6. And what was the other one? 3 pi over 2. Yeah, we got that. And the end points of your interval will be 0 and 2 pi. So we got that. So that will be the leftmost end will be 0. The rightmost end will be 2 pi because all this must be within 0 to 2 pi. Putting them in order is really important because we want to make sure that we are arranging them in the correct way on the number line. Again, if you're in doubt, check your use your unit circle to do this, or you can use algebra where you adjust all the denominators to be the same. Okay, so if you multiply up and down by 3, just to help you out here, pi over 6. If you change all the denominators to 6, okay, so that will be 3 pi over 6, 5 pi over 6, 9 pi over 6. So you can see the numerators are all increasing, 1, 3, 5, and 9. Okay. That helps us really to put them in the correct order. I insist on this just because I've seen too many errors made by students on this. Now I need to mark the end value, so 0, and then we have the 2 pi. This is, you know, actually they're not equally spaced as such. Okay, so I'm just going to just eyeball the positions. Then you have the 2 pi. Okay. So we have, regions now created because of these many points here, critical points here. So let me squeeze in the intervals. Zero to pi over 6. Okay, quite a squeeze there. Just again, I will let you choose a test point from each one of these intervals. Okay, and then you can determine the sign of f prime. Now, the signs are actually negative. Oh, if you are wondering how do I choose a point in this interval, the quickest way, or my suggestion is to set your calculator to the radian mode, and just go ahead and enter this as pi. Use the pi button from your calculator and do pi over 6, say. That comes out to be 0.5235, okay? So let me write that up here. Okay, and then pi over 2. You might have guessed this is going to be approximately 1.5 something because pi is 3.14. So this is going to be 1.57. Then you have 5 pi over 6, 2.617. 3 pi over 2, 4.7. And 2 pi will be 6.28. 3.14 times 2. Okay, so getting it in the decimal form will really help you because you can use a calculator to compute any value in between. So if you look at this 0.5 and 0.5 and 1, you can maybe choose a test point as 1. So you want to choose this interval as well. So in this interval, you could choose 0.2 or 0.3 and plug it in your calculator for your function, of course. So you're going to plug in sine squared 0.2 minus sine 0.2 minus 1, basically, to get your sign of, oh, I'm sorry, you'll have to plug it in f prime. Where were we? Yes, f prime right here. So 2 times sine 0.2 cosine 0.2 minus cosine 0.2. I apologize. You put it for f prime. So when you do that, this is the sign you'll get. Okay? So I have negative, positive, negative, positive, negative. You've seen before that it doesn't have to be a pattern like this, but here it does. And so we have the behavior of f. Let me quickly come here and say, well, that is decreasing, increasing, decreasing, increasing, decreasing. And I want to draw the number line. You can go back to that same number line to do it too, not a problem. And then perhaps we could use, so this is decreasing, 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 and decreasing. And this word, increasing, increasing. Now it's time for us to determine the extreme values. Okay. So there's a change in sign, decreasing to increasing, decreasing to increasing. So if you think of it too, you kind of trace it, decreasing to increasing. So it went from low to high. Okay? And if it's from decreasing, minus to plus, it means it has a local minimum, isn't it? Because it was decreasing and then it increased. So I'll just say minus to plus. I'll just simply say local min. Yeah, that way it's easy for us because this is minus and this is plus. And then it was increasing to decreasing. So this will be a local max. Decreasing to increasing. Local min. Increasing to decreasing. Local max. Got all of these now. And if we need to find the absolute max and absolute min from among these, so you'll have to plug this in, the values here. So this, we need to find f of pi over 6, basically. And f of pi over 6, if you compute it, comes back as negative 5 over 4. I need a little more room, so what I'm going to do is stretch this a little bit. So I'm going to keep all the mins together. F of 5 pi over 6. Compute this. That comes out to be negative 5 over 4. And local max, so f of pi over 2 is a negative 1. F of 2 pi over 2 is a positive 1. And of course you have to compute for this as well, right? F of 0 is negative 1. Remember, that's what we did for, we did use the critical points and the end points to find the absolute max, absolute min. So don't forget about the end points as well for this. So 2 pi, f of 2 pi will be negative 1. Both the end points are given as negative 1. All right, so then go ahead and look from among these, which one is the absolute lowest value, and that will become the local or absolute minimum, I should say. So what we see here is this and this. They both give us the same value. So that's the absolute minimum because we have two of them. So that's in plural. Or you could say absolute minimum is negative 5 over 4 and it occurs at pi over 6 and 5 pi over 6. And from among these, this seems to be the positive value. So that will be the absolute maximum. There's only one value that is a positive one. So that's absolute maximum there. And of course, we have the coordinates. So if you wanted to put the coordinates, it will be pi over 6 comma negative 5 over 4 and 5 pi over 6 comma negative 5 over 4. And here absolute max will be 3 pi over 2 comma 1. And if you were to kind of graph this, you can see that these are the places where you get this. So if you now you can pull out your calculator and you can actually compare your graph to see if all these pointers are matching up. And I have the graph here for you, as you can see. These were all happening down here, right? So there were two of these lowest values that matched, and so we got our absolute minimum or minima in these two places. And then you had absolute maximum at this point, but these also will be the local minimum and local maximum. There was a local maximum here at pi over 2. Yeah. So we do have, and of course, all these like negative 1, this place here, this value, negative 1, and this negative 1, they were also local minimum there. In this case, this was a local max, and this was a local min. We'll do the similar one for this type, where this function is h of x equals 2x cubed minus 18x. So same thing, we need to find the critical points and use them to determine the behavior of f, whether it's increasing or decreasing. Okay. Now we have h prime of x, which is 6x minus 18. I'm going to make it a little quicker here because I've explained the process enough, I think, that we can actually skip too much explanation and go on here. So x equals 3. I apologize, x squared equals 3, which means x is plus or minus root 3. Now we have the intervals. So let's draw this. The of part, I should say sine of it. Oh. Again, choose a test point there. You know, root 3 is, I think it's 1.732. And so go ahead and choose a value based on that. Okay, that's positive, negative, and positive. Behavior of f, not f prime, would be increasing, decreasing, increasing. Based on the first derivative test, the local extrema can be determined. If they are increasing, if it's going from increasing to decreasing, that means there is a, so it's going up and then coming down, so that must be a local max, right? Increasing and then it's decreasing, so it's like you have a maximum point. And then you have decreasing and then increasing. So it's decreasing and then it's increasing. So that means it's a local mon. And you need to find the coordinates for those. So plug them in. So find f of negative root 3. Find f of root 3. And if there were endpoints, like the previous example we were given from 0 to 2 pi, that interval is not given here. So you don't have any endpoints. So all you have to do is use these values to plug in your f function. Oh, there's no f, I'm sorry. I keep saying f here because it's h. I'm going to fix all these things back to h. H prime. H. Let's fix these also. Two times negative root 3 whole cube. And that comes up to be 12 root 3. This is negative 12 root 3. All right, so that is the absolute, no, that will be the local, because this assures local max and local min, right? So that is the coordinate for the local max, negative root 3 comma 12 root 3. And this is root 3 comma negative 12 root 3. So those will be your coordinates for these values. Now this is again going back to h. H is a polynomial function. It's a polynomial of degree 3. which means it goes endlessly. Therefore, these 2 points that you found as local max, local min would not become absolute max and absolute min, because your end points, the end behavior of your graph stretches indefinitely. Therefore, these are not the lowest or the highest points. So they will remain as local max and local min. So class, with that, we come to the end of this portion of monotonic functions and the first derivative test. There is still more to this. I will continue this section in the next lecture. And there we will be looking at concavity and curve sketching. We will put all these things together and be able to sketch a curve just from the basic information. All right, see you soon.